I do want to, in the last 5 minutes, get to something that you're going to need for your discussion problem tomorrow, which is internal flow energy balance. Okay, so let's see. What we want to talk about here is we've gone through like the boundary layers, the velocity profiles, the temperature profiles. What we need to do now is think about how the temperature develops in flow in an internal enclosed space. And there's different considerations that we want to think through there. But basically the approach is we need to do a control volume analysis, ODE, solve the ODE, apply a boundary condition, get to the results. So I just want to show you an example of how to do that because you kind of need to understand that process. All right, so for internal flow energy balance, again, what we're thinking about is the temperature of the fluid as it's going through. So for the temperature of the fluid, let's start off by drawing a control volume on our fluid. We're going to assume the temperature is uniform, right? Or there's an average temperature that we're modeling. So we're coming up with a function Tm of x. So let's look at what's going in. So what's going in, what's going out. So going in, we have some mass flow, m dot, times some enthalpy. So I'm going to call enthalpy I, because we use H for heat transfer coefficient. So this is m dot I at x. Leaving, we have m dot I at x plus dx. So it's m dot and I at x, m dot and I at x plus dx. And then maybe we have, in this case, some flux on our control volume. So let's say it's a constant flux, q dot double prime, and then the total that's going in is going to be q dot double prime times perimeter times dx. All right, so we're applying a flux to the tube. That tube, it's sort of forcing the flux into the fluid. The fluid's going to change its temperature. So we develop a model for this. By the way, I have a perimeter and I have a cross-sectional area associated with this. So let's do the energy balance. So this is m dot I at x plus q dot double prime perimeter AC minus m dot I at x plus dx equals 0. So using the same tricks as we used before, we're going to expand our m dot I at x plus dx into the Taylor series approximation. So that is m dot I x plus q dot double prime perimeter AC minus this thing here, which is m dot I at x plus d m dot I at x dx times dx equals 0. Okay, so then we cancel out our m dot I at x. Oh, sorry, did I miss a dx here? Q dot, wow, okay. Not AC, sorry about that. It's q dot perimeter dx. Q dot perimeter dx. Okay, that makes more sense. So now my dx's cancel out, right? So dx cancels here, dx cancels here. So if you guys will forgive me, I'm going to go like 2 minutes over if you don't mind, just to make sure you get through this for discussion. Okay, so we are left here with this ODE, which is d m dot I x dx is equal to q dot double prime times the perimeter. Right? So that's our ODE. If we assume that this problem has incompressible fluid, enthalpy can be modeled, or sort of the change in enthalpy can be modeled in terms of specific heat. So we would say m dot Cp dt m dx is equal to q dot double prime times the perimeter. Right? So this is my ODE for the fluid in terms of the mean temperature. All right, let me get through this one little bit here and then we'll be done. So what I want to do is now just solve this in terms of temperature. I suppose you probably can do this yourselves, but this is our ODE. Let's solve it for temperature. So dTm dx is equal to q dot double prime perimeter over m dot cp. So I'm going to integrate or bring dx over to the right and integrate both sides. And I'm going to get then, let's see, Tm is equal to q dot double prime perimeter m dot cp times x plus c1. All right, just solving that is a pretty simple equation to solve. So I apply a boundary condition. My boundary condition here is the inlet temperature, right, Tn. That's going to be equals C1, and I'm just applying that at x equals 0. So I say Tm is equal to Tn at x equals 0, which gives me Tn equals C1. And then the final solution here is Tm is equal to q dot double prime perimeter over m dot cp times x plus Tn, right? So this is what you're going to use to model temperature as a function of position in the event of a specified heat flux. All right, we'll go back next time and we'll solve this in terms of a specified wall temperature. All right, thank you.